Hi everyone. In this video we're going to look at how the first fundamental theorem can help us do a little bit better job of sketching antiderivatives. So here I'm being given f prime of x and I'm being asked to sketch f of x. But as you can see, I've already written, because my computer decided to eat the last recording I made, it would not change my process if I was naming the middle graph, the starting graph little f and the ending graph big F. So people will get a little messed up on notation as they're first starting in Calc 2, and what you want to focus on is not whether or not it's named the derivative or the function or the capital F. It's how far apart are they. So is one of these the derivative of the other? Is one of these the second derivative of the other? That's what really counts. In which direction am I going? Okay, so what the first fundamental theorem tells me is that if I want to integrate little f prime, then from a to b, then what I should get is the antiderivative function f evaluated at b minus the antiderivative function f evaluated at a. So this is the area under f prime, and we're claiming that that equals the change in y for f. So these areas that I'm given should actually be telling me very specifically how much my y value for my function changed. Okay, so if the area from 1 to 1.9-ish is 20, that means that when I graph down below, I need to make sure that my y value increases by 20 on that same interval. There's one more piece of info I need to go back up here and snag. I was given a y-intercept. This is that whole plus c thing. If I wasn't given the y-intercept, I get to choose where to start. It's totally up to me. But here, I'm being told to start at 0, 5. Oh, I think I just went through all of that without even acknowledging that this is negative. So the area is 20, but the integral from 0 to 1.9 is negative. So change my mind. I don't want my y value to increase by 20. I actually want it to decrease by 20. So if I go over to about 1.9, my y value should be down at negative 15. So my y value was 5. It is now dropped to negative 15. When I then look at this area from, it looks like about 1.9 to about 5.1, that's telling me that the integral from 1.9 to 5.1 of f prime is equal to 30. So down below on the graph of f, my y value should increase by 30. So if I go over to 5.1, my y value should have gone up from negative 15 to positive 15. And then we have this last little stretch, so we could say the integral from 5.1 to, looks like it hits pretty much at 6 of f prime is negative 4, so my y value needs to drop down just a little bit. I claimed I was up at 15. Oh, I don't know why I just moved that point over. Yay. Okay, so if I'm dropping 4, I need to be down at 11, so my point should be right about here. So now I have 4 really nice points that I can use. That's not all I use. I still need all my other stuff as well, so this is a good review if you struggled a little bit with sketching antiderivatives. So I can say, as well as knowing that these points, I also know the behavior of f between the points. So whenever f prime is negative, the function will be decreasing. Whenever f prime is positive, the function will be increasing. So we know the graph needs to go down, 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 down until I get to this point at the bottom. So that should be some sort of minimum. Then it needs to go up, 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 up until I get to this point at the top, which means that's some sort of maximum, local maximum, maybe global maximum, I don't know. It looks like it'll be global, at least for what I'm seeing here. If there's more to the function, then there might be some other ones. I can also talk about concavity. So remember, here, let me pick a different color. When f prime, so this is going to be f double prime that I'm summarizing. When f prime is decreasing, f double prime is negative, because now we're talking about the derivative of f prime. So negative slopes equal negative f double prime. Positive slope, which goes for quite a while, equals positive f double prime. Back to negative slopes. There's negative f double prime. And then here, splits. Back to positive slopes. And I don't know if that actually goes through or not. Positive f double prime. So by looking at the slopes on f prime, I can describe f double prime. If I want to tie f double prime back to f prime, it's concavity. So now I know that my function is decreasing concave down up until I get to about 0.5. And I don't know exactly what the y-coordinate of that point is, but I think what I just said is definitely a fair statement. And okay, so decreasing concave down for a little bit. And then from 0.5 to just before 2, I see decreasing concave up. So decreasing again is that the derivative is negative. Concave up is that the second derivative is positive. So decreasing concave up until I hit my minimum. Okay, and then from 2 to about 3.5 is, I think, my next split. So from 2 to 5-ish, not quite exactly, the derivative is positive, so I know I'm increasing, but concavity is going to change. So from 2 to about 3.5, my function is increasing. It is also concave up. So I'm going to go increasing concave up until I hit, what did I say, 3.5-ish? 3.5. And then it is totally coincidence that I'm making these inflection points happen at the x-axis. That's not actually on purpose or something you should assume. It's just how I'm drawing. Let's see. And then from 3.5 to 5, my derivative's still positive, so my function's still increasing. So that's the positive y values that I'm getting here. But now it's getting smaller, so slopes are positive, getting smaller. That means increasing concave down. And then I should hit that maximum right at 5. And after that, I'm going to go decreasing, right? So this is decreasing, decreasing. And again, that's just looking at y values, because these are negative y values. My function f should be decreasing. Since the derivative is also getting smaller, that means the second derivative is negative. So this is decreasing concave down. So slopes are negative and getting more negative. That's decreasing concave down. And that happens until about 5.5. And then this last stretch, slopes are still negative, but they're now getting less negative. So this is flattening out, and it looks like it should be horizontal tangent right at the end. So this is a slightly more accurate sketch of an antiderivative. We can improve a little bit on our old methods. Thanks for watching.